Okay, some more problems from section 9.3, and this is number 3, and our function was f of x equals 5 sine of negative x, and we know from our trigonometric equivalencies, remember the sine of negative x, if I take that and I put that in the fourth quadrant, that's going to be, remember sine's negative in the fourth quadrant, so the sine of negative x is negative the sine of x, because the sine is positive in the first quadrant, but sine of negative x would put it down in the fourth quadrant, and that would make it negative, so that's the sine of negative x is negative sine of x. The cosine of negative x is the cosine of x, because cosine is positive in the first and the fourth quadrant, so that stays the same. So that's the interesting one. But we can make it a little bit easier like this, so we don't have to worry about this inside. And then we just take our derivatives, and that's what I did. I took my 4 derivatives. I start with a minus 5, and the derivative of sine is cosine. Derivative of cosine is negative sine, so that negative times the negative x is positive, and the 5 just stays out in front because there's nothing in here. There's no function. It's just a straight x. And this is just going to be the derivative of sine is the cosine, and the derivative of cosine is negative sine. And there we go. And we evaluate those at 0, as we did in the first two problems. Sine of 0 is 0, cosine of 0 is 1, so that's negative 5. Sine of 0 is 0, goes away. Cosine of 0 is 1, so that's just 5, and sine of 0 is 0 goes away. I wrote down my general terms. And I'm sure a lot of you won't want to bother, but it would be a good idea. Always write it down, just get more practice. So you know that Taylor formula, just forwards and backwards. Okay, then we have P of 4. Then again, the first, third, and fifth, 1, 3, and 5 go away, so I just have these two terms. All right, the first derivative was negative 5, and this was x. And the third derivative was 5, and that was 5, and that's x cubed over 3 factorial. We can work it out. That's 6, so that's 5, 6, x cubed. And this is negative 5x, and I just evaluated those at 0.2, and this is what I got. And check these because they're pretty close. I checked number 2, and that was all the way out to 4 places, pretty accurate. And again, these are transcendental functions. I mean, there's no way to figure out what the sine of 0.2 is. All right, but you know, you could do it using these functions, though, these series. So, and it's pretty accurate because the series is about x equals 0, and 0.2 is real close to 0. If I was trying to find the sine of 2, that would be different. That would be out of ways. Okay, but 0.2 is much closer to 0, and the closer you get to 0, the better you're going to have your approximation. Okay, let's take a look at number 4. Now, number 4, we could get away with a little bit of previous work. So here's number 4, and we wanted to find the natural log. The function was f of x was equal to the natural log of 1 plus x squared. But we know the Taylor expansion from page 491 from our Maclaurin's expansion. From page 491, we know from our Maclaurin's table that the natural log of 1 plus x was just x minus x squared over 2 plus x to the third over 3, and this is our general term. So I can just substitute. We'll have the same integral convergence, so I just put x squared in here. So every time I see an x, I put an x squared, and that's a expansion of my new function. And I just kind of worked it out a little bit here. X squared squared to the third is 6, etc. And we put an x squared actually in the general term. The n stays the same. The x term just becomes x to the 2n. Now, the curious thing about this is my exponents were, I went from 2, 4, 6, so wasn't really too sure what my fourth order would be, if the order was going to follow the exponents. It usually does. So, but I just checked it out. So what I did was I went back and I just did a couple of them just to check and see what would happen. So I used f of x equals the log of 1 plus x squared, and I evaluated that at 0, and that's just the natural log of 1, which is 0. Then I took the first derivative, and I got 2x over 1 plus x squared, and I evaluated that at 0, and I got 0 again, 0 over 1. And then I did the second derivative, and I got 2, and I just checked that to see if that term would work out. So I kind of did this in pencil just because I wanted to make sure, and I put that in the Taylor form, f double prime 0, x squared over 2 factorial, and those 2's cancel, so I got x squared, which was this one, which was actually, would have been my third term. So it looks like the order was matching the exponents. So I wanted order 4, so I just needed these two. This would give me order 4, because the others would zero out if I did it the long way. So when you substitute it in, it works out, and then it does match, it just follows the exponents. Okay? And then I just evaluated this at point 2 to get my approximation. F of point 2 is approximately p, so 4.2, and then I just put the point 2. And then I could have done this, easily without a calculator. Well, wouldn't be so easy, but I would get that. But I did it with my calculator, and no problem. Okay? 0.0392. Okay? So the order did match the exponents. All right? And then number 5, kind of have to do that the standard way, and I think you can follow the work. All right, so my function was 1 minus x to the negative 2. So remember, it's going to be u to the n du, and the derivative of this is always going to be a negative. And I'm going to be multiplying by a negative, so that negative from the chain rule times the negative from the power rule is going to cancel out, so these are all going to be plus. So like the first one, I would multiply by a negative 2 times this to the negative 3 times the derivative of that, which is negative 1, so that negative becomes a positive. So it just ends up being 2 times 1, 3 times 2, 4 times 6, 5 times 24. So those are my derivatives, and I want to evaluate it at 0. If I put zeros in here, I just get 1 to various powers, which is just 1. So it's just going to be the derivatives of the functions evaluated at 0 would just be these coefficients: 1, 2, 6, 24, 120. And then again, I wrote my general form out. See. The only time I didn't have to write that out was from the number 4 that I kind of inherited it, but otherwise, I write it out every time, and I do it the long way. And then I substitute in. There's my first derivative, second derivative. There's my value of my function, my 0 derivative, first, second, third, and fourth derivatives from up here. And then I simplified, because this was 2 factorial 6, 3 factorial, and 24. So I simplified. These were simplified out. 2 goes into 6 3 times, 6 goes into 24 4 times, and 24 goes into 125 times. So there is my function, and then I just wanted to evaluate that at point 2 to get my approximation. So I put the point 2 in each of these terms. Every time I see an x, I put a point 2. Worked that out on my calculator, and I got P sub 4.2 is 1.56, and that was an approximation to f of 0.2. Okay. So if you do your work neat and orderly, there's no problem. Hopefully.